Good morning, student. So we would like to talk about chain rule. The chain rule. So it's one of the most powerful rule that is going to help us to deal with a complicated function, especially a composite function. Remember, we did composite functions in our M1511, the algebra part. So now you will see now we are going to apply those composite functions here, but now we want to know how to differentiate those functions or how to find the derivatives of those composite functions, and we'll be using nothing else except the chain rule here for now. So what is a chain rule? Suppose you are asked to differentiate this function. The first temptation to do is to start writing f of x in the form of x squared plus 1 and then raised to the power half, and then trying to get the derivative directly, and then you start bringing the power down using the power rule, and then you bring the power down, and then you keep your term here, which is x squared plus 1, and then now you subtract 1 from the power. Then when you subtract 1 from half, you get minus half. And then this is just once we have the power rule, but this is wrong. This is not a correct answer. It's only good if you have f of x defined in terms of x to the power n. That's where we can apply our power rule straight away. But in this case, we need to do something, a little bit of work, so that we can come back and be able to get derivative of f of x. So what we want, first thing, what we need to realize is that the function f of x, we can think of it as being defined in terms of two functions. There is this inner function here, which is x squared plus 1, and also we have the square root outside. So we can think of the inner function to be another function, and then it somehow takes us to a composite function. So we are talking about a composite function, whereby we can let the inner function to be u. Once you have let the inner function to be u, then it means if you are looking for f of x, actually you are looking for a function outer there, which we define as f of u, which is just nothing but square root of u, but u, remember, is the inner function, which is nothing but x squared plus 1. So it means now we can define f as a composite function. We can define f as f of g of x, where g of x is nothing but u. So here we have just nothing but u. So that's what we see, and we know that we can also write this in terms of this notation. So that's what we know for now, and keep that in mind because it's going to be very important as we go along. So let's define chain rule. So suppose you have that function that we just talked about, which is in the form of f of g of x, and first we assume that g is differentiable at x and f is also differentiable at g of x or at u. Remember, we can let g of x to be u, which is the inner function in our composite function. Then we define our composite function to be this form, and we define our derivative of f to be nothing but this expression. So what are we saying? We are saying here that if you are to differentiate this function, let the inner function to be u, and then differentiate f with respect to u to get a new expression. And then remember, you need to take the derivative of u, but u is nothing but g of x, so we can take the derivative of g of x. So you have a product here. The first you take derivative of f with respect to u, and then now you take the derivative of u with respect to x. So these are the two functions that are multiplying. So that's the first formula that we have. But Leibniz also had some kind of a different way of writing the same thing. So what is he had in mind, he said, let y to be equal to f of u, and then similarly let u to be g of x like we did before. But now that y is f of u, let me pretend as if I'm looking for dy dx. And then immediately once you do that, you look at the function f, you find that f is not directly a function of x. Interesting. So that means we can't go straight and differentiate f with respect to x. So we need to first start by differentiating f, which is y, with respect to u, because it's a function of u. But keep in mind that we want the derivative of y with respect to x. So u also now we can see it's a function of x. So we can differentiate now u with respect to x. These are the two things. So you're looking for dy dx, and then you try to differentiate that function of y. You find that y actually is a function of u, so you start first by differentiating y with respect to u. But after you have done that, you find that actually you haven't found yet dy dx. So you need again now to differentiate u, but u now with respect to what? To x. So at the end of the day, we find that actually chain rule is just a product of the two derivatives. You get this derivative, you multiply by this derivative. And that's exactly what we got previously, a product of two derivatives, which define the chain rule. That's one thing. Actually, if you look inside this chain rule, you may be tempted to see something. If you were to take this as a fraction, you could see that you could think of dy du as if du can cancel du, and then you are still left with dy dx, which is probably what we have this side. But we normally don't treat it as a fraction. We treat it as a derivative of y with respect to u, and then derivative of u with respect to x. Keep that in mind. So that's what we are saying here, that if we were to think about them as that, you may find that du will cancel out. But remember, we don't know du. Therefore, du is not defined. Therefore, we cannot actually consider it just like that. Be careful. So let's look at that example that we had at the beginning, which was very complex, which is nothing but f of x, and we can write f of x as nothing but x squared plus 1, x squared plus 1, all raised to the power half. All raised to the power half. So what is the first step now? Let the term that is inside here, which is x squared plus 1, to be u. That's the first step that we are doing here. So that now, once we have done that, it means we can rewrite your f. So once you have let the inside term to be u, you can rewrite your f as f of x to be equals to nothing but, instead of f of x squared plus 1, it will be just f of u, the small f of u. So we can even think of u to be equals to nothing but g of x here. So our u is nothing but g of x here. So remember the chain rule. Chain rule says if you are looking for dy dx, so you take your function now, you find f prime with respect to g or u, but now multiply that with g being derived with respect to x. So that's one thing. So we take our f, we derive with respect to u. If we derive that with respect to u, you have nothing but remember f of u is nothing but u to the power half. So if we take the derivative here, it means f prime of u would be equals to, you bring half down, and then you take u, and then you take half minus 1. Then the result of that, it becomes half u to the power minus half. So that's what we have. And because of minus, you can rewrite this like this using the rules of exponents that you know very well. So now, the next thing, remember, we have now found f prime of g, which is right here. So we need g of x. So we know g of x is given by that. Now we need the derivative of that. So you take the derivative of that, you know the derivative of a constant is 0. So we are now concentrating on x squared. You take x squared, you bring down 2, and then you have x to the power 2 minus 1. Just using the power rule, you get this. Then now you bring them together with this formula. When you bring them together, you can bring them in terms of u and x, but at the end of the day, remember, u was introduced by you as a student. So your original question did not have u. So finally, you must replace u with what u is in terms of x. So that means you do back substitution. So you bring back what is u here, because you know that this is 2 square root of u. So it will be 2 square root of u. What is our u? Is x squared plus 1. But multiplied by g of x is nothing but 2x. So this one you don't need to do anything. Then you can leave it in this form. So remember to leave the answer with a variable that was originally there. The one that you introduce to simplify life, to try to use chain rule. At the end of the day, you must get rid of that variable that you have introduced, and then leave your answer in terms of the original variable. Do back the substitution. Okay. Now let's use that other formula, because now we use the other one. So let's use the one where we know that dy dx, and see if we can get the same answer. Okay, instead of differentiating y directly, remember y now is a function of u. So we'll start first by saying dy du, and then we multiply by du dx. If we do that, dy du, actual dy du is the same as the previous one. So you still get this portion for dy du, and then this part, which is du dx. Remember our u, which last time we called g of x, so it's still this portion. Then you take the derivative of u, you get 2x. Now remember to do back substitution. You bring back what is u, then you get this new expression. Your u is nothing but x squared plus 1. Then you simplify, you end up here. The two cancel. The same answer as the previously. So these two answers are the same. So it's up to you as a student, which one you feel more comfortable with between the two formulas. But use them appropriately. Use them appropriately. The previous method, there is always one temptation that students used to do, and that used to result with some errors. We'll see as we go along that that temptation is there, which student used to apply, and it normally results in some errors. But now let's get to the next one. So what are we saying here? We are saying, remember that dy dx is nothing but derivative of y as a function of x. So it means we are taking derivative of y with respect to x. And then dy du, we are taking derivative of y with respect to u. That's what you should keep in mind inside the chain rule. So when we look for dy du, we are taking derivative of the function y, but with respect to u. So it means somehow we have done some substitution to introduce the variable u. Otherwise, we might find ourselves into trouble. Okay, so that's what we have now. So the function, derivative of the function, we found it to be this one, as opposed to dy du, which we found it to be this one. And remember, for dy du, now we introduced a new notation here of the small f of u, which was f of u at the beginning. So we started writing the big F in terms of as f of u. So that's what we had previously. So in general, you can even work with the, suppose you are given y to be equal to sine of u, and then we assume that u is also a function of x, which is differentiable function of x. Now we can still apply chain rule again. Dy dx, to get dy dx, we need to first start by differentiating dy with respect to u, because now y depend on u. And then now after finding dy du, now we need to multiply by du dx, because now u depend on x. So if we find dy du, we find that dy du is nothing but cosine of x, but you still have du dx. If somebody gives you what is u, you can apply it directly, but for now, let's leave it as just du dx until somebody gives you a function du, then you can be able to substitute here. And we can do a lot of functions, including quotient of trigonometric functions, product of trigonometric functions, and trigonometric functions raised to power something. So chain rule, this is chain rule. It's a very simple rule. But now let's look at the general form of the power rule, or a function which is written in as g of x raised to the n. Now you can still let the inner function, which is g of x, let this one to be u. Now you have your y to be equals to f of u, which is equal to u to the power n, where we let it to be this one. So the same way that we did previously, dy dx is the same as differentiating dy with respect to u, and then remember to differentiate du with respect to x, and then multiply the two. So when you differentiate dy du, remember your y is here, so your y is here, and then you bring down the power, that means you bring down n, and then you have u to the power n minus 1. That is the derivative of y with respect to u, this portion. You also have du dx. We can leave it like that, or remember that du dx is nothing but the derivative of g with respect to x. So this is a bit more general chain rule for the power function, for the function raised to some power n. And we still have it here, which still looks nicely, but you can, instead of u, you can still replace u with g of x, and then you still have this function here. You have n g of x raised to the power n minus 1, but multiplied by the derivative of g of x. That's one thing which you need to keep in mind. So let's look at if we can apply this to a simple example. Y is equal to x cubed minus 1 raised to power 100. Looks like a monster, but our n in this case we can take it to be 100. And then now do the derivative. Remember, we can take the derivative of the outer function. That means you take 100 down, and then you have 100 minus 1, which is 99. But now remember, you still have to take the derivative of the inner function, which is this portion, and then multiply that with this. So when you take the derivative of the inner function, you get 3x squared. So it means here you have the derivative. It looks previously, if we compare previously, we would let this part to be u. So it's like this is nothing but dy du, this portion. And then this last part is nothing but du dx. That's how it looks like. And then now you bring back what is u, then you still get back x squared minus 3 raised to the power 99. Finally, when you simplify and then multiply by 3, you end up with this expression. Simple as that. So this is good news with chain rule. This is good news with chain rule. And now here they are trying to show you why do we even call this part chain rule, because now you can make a chain of different function. You can compose one function with another, and then that function be composed with another function. So you have f being composed with g, and then you have g being composed with h. And then now we can start letting the inner function to be x, and then let the function in the middle to be u, and then the outer function remain as f. So in that case, it means if you want to find the dy dt, remember the aim is to find dy dt. So if you try to find dy dt, the first thing you try to get into y, you find that y is a function of u, so you have to start with dy du. And then when you look into the function, you find that u is a function of x. So it means you can only differentiate u's back to x first. And then now when you get inside into x, you find that x is a function of time. So now you have dx with respect to dt. And finally, you have made a long chain, dy du, du dx, and then dx dt. So you can see from here, you can apply this formula to a longer chain of functions which are composed of each other. So we can have a function composed inside another function, and then that results with a new function which is also composed into another function. Then we can make a long chain. So that's the chain rule for you. So this is all about the chain rule, as simple as that. So please, with this, work the problems for this week. And what you should know now today you should be able now to deal with composite functions, be able to get the derivative of composite functions. Although I know you're already ahead, you already know that, but be able to get the derivative of composite function applying chain rule. That's one thing. Next, we are going to talk about implicit differentiation. So that will be the topic before the last, which will be the L'Hospital. Then we have test 1, which you remember from our message that test 1 will be next week, Friday, 26. So get ready, prepare as much as possible. Good luck.